In the last video, we introduced statics puzzles. Puzzles where the forces and torques cancel out and no motion occurs. In this video, we will explore statics puzzles in 2 dimensions. When forces are not pointed directly along the x or y axes, we sometimes need to break them into components before we can solve the statics puzzle. Consider this puzzle. A 2 kilogram, 0.2 meter deep shelf is attached to a wall via a hinge. The outer edge of the shelf is connected to a chain that is angled at 30 degrees above the horizontal. What is the normal force at the hinge? In this question, we have a shelf that is hinged to the wall. Something like that. And it is supported by a chain. Something like that. Now, let us write in all of the forces that are occurring. Or better still, let's wait on the forces for just a second and let us first draw in all of the axes that are relevant here. So, there's the x-axis. There's the y-axis. Some additional bits of information. This angle over here, which I'm going to draw in green, is 30 degrees. The mass of this shelf is 2 kilograms. And there are 3 forces acting. One is the weight of the shelf. A second is the tension in the chain. And the third is the normal force. You might wonder why I've drawn the normal force like this. The answer is because the chain is pulling this basically leftwards, or at least it has a component that is leftwards. The normal force has to have a component that is rightwards, but it also has to have a component that is upwards in order to be able to counterbalance the both of these 2 remaining forces, both the weight and the tension. Now, because we have forces which are drawn in a fairly complex way, it will help us to draw a free body diagram as well. So let's go ahead and do that. The weight is going to point down. The normal force is going to point at this angle over here. And the tension is going to point at this angle over here. So I'm going to set my axes. And I'm going to break these 2 forces into their components. So this now becomes very similar to a force question that we have seen many, many times before. Here's the weight. Here's the tension. Here is the normal force. This tension is angled at 30 degrees, so this component over here is going to be tension cos 30. And this over here would be tension sine 30. Now the cosine of 30 is 0.866. So I could write this like this, or maybe I'll even hold off on that. I will solve them I won't solve them on the free body diagram itself. Now, we do not know what this angle over here is. Like I said, we know that this is 30. We don't know what this angle is. But I can say that this side over here must be normal sub y, and this side over here must be normal sub x. So, and it is basically these two, normal sub y and normal sub x, which is what we are looking for. So now that we have the free body diagram, we are now ready to start writing out the force balance. And since it occurs in both x and y, we need to solve the force balance in both directions. Let's start with x. In the x direction, we have normal in the rightwards direction and t cos 30 in the leftwards direction. So the total force here is going to be equal to normal sub x minus t cos 30 degrees. And those two have to add up to 0 because the total force in x has to add up to 0. So we could simplify this a little bit. The cosine of 30 degrees happens to be 0.866. So if I were to move this around to the other side, I could rewrite this as follows. Normal sub x is equal to 0.866 times whatever the size of the tension is, which we have not yet solved for. So this is the relationship that we have gotten from the x direction. Now next, what about the y direction? In the y direction, the total force is given by, let's see, there's t sine 30 pointed upwards, there's normal force in y also pointed upwards, and there's weight pointed downwards. So let's write those out. There is the normal force in y, I will start with that, plus t sine 30 minus the weight. And all of that's equal to 0. Now, we can easily solve for the weight. So let's go ahead and do that. Weight is equal to mass times gravity, which is equal to 2 times 9.81, which is equal to 19.62. The sine of 30 happens to be 0.5. So if I plug in 19.62 for weight and I move it over to the other side, then this entire equation now becomes normal sub y plus 0.5 times the tension is equal to 19.62. Alright, so now we have a relationship between the tension, which is currently unknown, the normal force in x, and the normal force in y. We just need one more relationship between these two, or between these three, I should say, before we will be able to solve it. And that relationship is going to come from the torque balance. Look at the way that I have set up my axes over here. The x-axis is in line with the shelf and the y-axis is in line with the wall. That means the normal force is passing through the origin, so it exerts no torque. But the weight force does exert a torque, and the tension force also exerts a torque. So what we're going to do is we're going to solve for what those torques are, and we're going to start writing them over here. So remember what the rule is for torque. That is that
torque is equal to the size of the lever arm multiplied by the size of the force multiplied by the sine of the angle between them. So let's start applying those to the weight force and then to the tension force. So torque of the weight force, that's going to be given by how far is the weight force away from the hinge. Well, there's actually one piece of information which I had forgotten to put down, and that is the fact that the length of this shelf is 0.2 meters. Because it's uniform, the weight force is going to occur at its geometric center, which is 0.1 meters. The size of the weight force is 19.62. And now we need to find the angle. The lever arm is rightwards, the weight force is downwards. That is a 90-degree angle. Okay. Sine of 90 is 1. So that gives us 0.1 times 19.62 times sine of 90. So that gives us that the torque being caused by the weight force is equal to 1.962. Now the last question is this going to be a clockwise torque or is it a counterclockwise torque? The answer is this force by itself would tend to rotate this object clockwise. This is a negative torque. So we have now figured out the torque that is coming from the weight. Let's do something similar for the tension force. The length of the shelf, or the tension force is being exerted at the full end of the shelf, so that's 0.2. The size of the tension force is unknown. And the angle over here is 30 degrees. So that means that the torque being caused by the tension force is 0.2 times sine of 30. Sine of 30 happens to be 0.5, so that's half. 0.2 times half gives us 0.1, and thus we get that the torque caused by the tension is 0.1 of the tension force. Okay, so now that we have all of this, we're ready to apply a torque balance. Now, the way we're going to go ahead and do this is to write out that the total torque is equal to the positive torque, that's torque coming from the tension, minus the negative torque, which is torque coming from the weight. And all of that's equal to 0. So putting all of this together, we get 0.1 times the tension minus the torque being caused by the weight, which is 1.962, is equal to 0. So this is now our torque balance. And now we suddenly see that it is extremely easy to figure out what the components, first of all, what the tension is, and second of all, what the components are of the normal force. So, moving this around a little bit, I get 0.1 times the tension would be equal to 1.962, or equivalently, the tension becomes equal to 19.62 newtons. So that is our first solution. Now, I can take this solution and I can put it into this equation over here to solve for the normal force in y. The normal force in y plus 0.5 times 19.62, that's the size of the tension force, gives me 19.62. Half of 19.62 is 9.8. I can then subtract 9.8 from both sides, and that gives me that the size of the normal force in y must be 9.81. That would be newtons. Okay, and the way that we solved this was by taking this equation and combining it with this equation. So these two equations put together give us this expression, and we can solve for the normal force in y. Finally, to solve for the normal force in x. The normal force in x is equal to 0.866 times the tension, which we know is 19.62. So that's going to work out to 866 times 19.62 is 16.99. The normal force in x is 17, let's call it 17 newtons. 16.99 if we want to be really exact about it. So let's go through how we solved this whole question. We started by drawing the picture, of course, and then drawing the free body diagram. We worked out the sum of forces in x, and we got this expression relating normal in x to tension. We did the same thing in y, that is the force balance in y, and set it to 0, and we got normal in y plus half of tension equals 19.62. Then we found out what the torques were of the weight and the tension force, and we put them into a torque balance over here. That gives us a relationship that easily lets us find the size of the tension. And once we have the size of the tension, we can easily use that in concert with the force balances in order to work out how big the components of the normal force must be. So that then is the way that we solved for the normal force without even knowing how big the tension force was.
In this video, we saw several examples of statics puzzles. In the next video, we will explore rotational energy.
In this question, we have a wall, we have the ground, and we have a ladder which is leaning against the wall like this. I'm going to start by drawing in the forces. The ladder feels a normal force from the ground. Let's call it M sub g. It feels a force of friction with the ground. That would be static friction, since of course it's not moving. That's F sub s. There is normal force from the wall. Let's call that N sub w. And finally, there's the weight force, which is going to be pointed downwards from the center of the ladder. Let's call that W. Next, let us draw in the axes. I'm going to set my origin at this point here, And the reason for that is there are two forces passing through this point. If I set it over here, those torques will both cancel out and it'll be a much easier question to solve. So in the y direction, it looks like this. And in the x direction, it looks like that. Now, the next thing is to write in all of the information that we know. This angle here is 60 degrees. This angle here is 30 degrees. This angle here is also 30 degrees. And this angle here is 60 degrees. We know this from a little bit of geometry. These two angles are similar to each other, and these two angles are on opposite sides of the ladder, so they'll work out to be 60 degrees each. Now, what other information were we told? We were told that the mass of the ladder is 10 kilograms, and that the length of the ladder is 3 meters. That length is going to become important because of the relative locations of the weight force and of the normal force from the wall. Because this diagram would be too crowded if I drew it in, I'll just make a point here of saying the overall length of this ladder is 3 meters and the weight force is being exerted at 1.5 meters. So maybe I could write it in over here. This position is 3 meters from the origin, and this position here is 1.5 meters from the origin. Okay, so that's pretty much all of the information that we've been told. It's a lot of information we were told. So knowing all of this information, let us solve for what the force balance is in X. In X, the total force is equal to the static friction pointing rightwards minus the normal force from the wall pointing leftwards. And all of that's equal to 0. Now, we don't know what the value of the static friction is. What we do know, however, is that static friction has to take on a minimum value which is equal to the coefficient of static friction times the normal force from the ground. So plugging this information into the force balance, and given the fact that we don't know any of the other variables over here, we can say that mu sub s multiplied by the normal force from the ground is equal to, I can move the normal force from the wall on the other side, this. So this gives us the first relationship between the normal force from the ground, the normal force from the wall, and static friction. Cool. Now, let's go ahead and let's do something similar for y. In y, there are two forces acting. The total force in y is equal to the normal force from the ground pointed up and the weight force pointed down. Okay, the weight force is equal to mass times gravity. The mass is 10. The gravity is 9.81. So that means that the weight force is equal to 10 times 9.81 is 98.1. And we've just now solved for the normal force due to the ground, because these two forces add up to 0. Therefore, the normal force from the ground must also be 98.1. So, putting this information in, weight force of 98.1, normal force of 98.1. And this information comes from the fact that the normal force minus the weight force was equal to 0. So we have just now solved for the size of the normal force from the ground. Let's keep going. We are now ready to start applying the torque balance. There are only two torques in this question because normal force from the ground passes through the origin, static friction also passes through the origin, so their torques are 0. That just leaves weight and normal from the wall. The rule is that torque is equal to lever arm multiplied by the size of the force multiplied by the sine of the angle between them. So, the torque coming from the wall is equal to the location of the weight force relative to the origin, that would be 1.5 meters, times the size of the weight force. We already worked out that the weight force was 98.1, times the sine of the angle between them, which is in this case 30 degrees. So what does that work out to? 1.5 times 98.1 times the sine of 30 degrees, 73.58. So that's the size of this torque. And is this a clockwise torque or a counterclockwise torque? This is a clockwise torque. So I need to correctly say negative 73.8. So this is the torque coming from the weight force. I've symbolized this as torque sub W. The other torque is going to come from the normal force acting at the wall. So that would be torque, I'm going to call this torque NW, torque normal from the wall, which is equal to the distance from this force to the origin, multiplied by whatever the size of this normal force is. We do not know this one yet. Multiplied by the sine of the angle between them. From the ladder to the normal force is 60 degrees. And that's going to work out to 3 multiplied by the sine of 60 is 2.598. So that's about 2.6. I'm going to call this 2.6 times however big the normal force at the wall is. And this is going to be a counterclockwise torque. That means that this is positive. So now we have worked out how big all of the torques are, and we are ready to perform our torque balance. Now, the sum of the torques is going to be equal to the counterclockwise torque from the normal force at the wall, tau NW, minus the clockwise torque coming from the weight. And the difference between those is going to be 0. Now, let's plug in everything that we know. The torque of the normal force from the wall is 2.6 times that normal force. The torque from the weight is going to move over to the other side and it's going to become positive, so that would be positive 73.58. And this now becomes very easy to solve. We can now find that the normal force from the wall is equal to 73.58 divided by 2.6 basically is 28.32. So we've now solved for the normal force from the wall. Last is to find out what the coefficient of static friction is. And we can use this equation over here to interrelate the normal force from the ground, the normal force from the wall, and the force of static friction. So what we know is the force of static friction multiplied by normal force from the ground, that's 98.1, is equal to normal force from the wall, that's 28.32. So 28.32 divided by 98.1, that gives us 0.29 approximately. So this then is the solution. This is the value of the coefficient of static friction. So let's quickly review how we solved this. We started by creating a force balance in X that gave us this expression that relates mu sub S to the two normal forces. We then set up a force balance in Y, which let us solve for the weight and very easily to solve for the normal force from the ground. And finally, we set up a torque balance using the torque caused by the weight, clockwise, and the torque caused by the normal force at the wall, counterclockwise. These add up to 0, and we could easily find the normal force from the wall. Finally, we put all of this information together. The normal force from the wall, the value of mu sub S, or the relationship between that and the two normal forces, and the value of the normal force from the ground, and we solved for what mu sub S was equal to. It's equal to 0.29.
In this video, we saw several examples of statics puzzles. In the next video, we will explore rotational energy.